Hello everyone, welcome to my lecture on elementary differential equations. This is video number 16 for chapter 2. In this video, we will discuss autonomous equations. Let's first have a definition for such an equation. Okay, so the definition is quite simple. An autonomous equation is here we only consider first order equations, is an equation of the form that y prime equals f of y. So here note that the function f here, that is the first derivative of y, depends only on y and there is no t in it. So these type of equations would arise in modelings of physical phenomena where the behavior, say the rate of change of the quantity you are studying, is not depending specifically on time, but depend on the state, meaning how the value of y. Let's look at the simplest example. Y prime equals ry. Depending on the sign of the r, we could have either exponential growth or decay, and we studied this already, and the solution is just an exponential function here, where y naught here is the initial condition, that is y at 0 is y naught. So even though the right-hand side of the ODE doesn't depend on t, your solution is a function of t. From our study of the directional field of ODE, we have seen such examples, and we notice that the zeros of the function f of y are of particular interest. So here is a definition for these. So the zeros of these f, there might be one, there might be multiple, or none, depending on your f. If you find one, these are called critical points. They are also called equilibrium points, or they are called equilibrium solutions. So these terms are used in different contexts. So why are such y's called equilibrium solutions? Well, the reason probably we already know. You recall in our study of directional field, we have observed that if for some value y naught, for example, initially, f of y naught is 0, then y prime is 0 and y remains constant. And yt equals to y naught is a constant solution. So if this is a time-depending problem and your solution settles at a value and does not change anymore, we call this an equilibrium. An interesting question to ask here is, if you have an equilibrium, is it stable or unstable? So that's a question in itself, needs some explanation, namely the definition of stability or instability. So we'll look at some example first. Okay, let's look at an example. So my equation is y prime equals y times y minus 2. So that's my f of y. And let's locate the critical points. So it's already written in the factorized form, so it's very easy to find two critical points. One is when y is 0, and the second is when y minus 2 is 0, so when y2 is 2. Okay, so here on the left, what I present here is the graph of f of y, this function here. And you see that this is a polynomial of degree 2, so it's a parabola. And when y is 0, it's 0, so you have this point. and when y is 2, it's 0. So these are the two zeros. And this is the line on the x-axis where f is 0. So from this graph, we see the following. Consider on the interval where y is less than 0, meaning on the left of here. Here we see the graph of f is above the axis, so f is bigger than 0, which means y prime is bigger than 0. Then in the solution of the differential equation, as time goes, y would increase. So therefore we draw a little arrow pointing to the right to indicate the direction of the change of the y value. And now let's consider the interval between 0 and 2. Here the graph of f is below the axis, so f is negative, and therefore y prime is negative. So if your value, y value, is on this interval, then as time goes, it will decrease, so it will go to the left, and therefore the point to the left arrow here. And similarly, for the case when y is bigger than 2, and then the fy is bigger than 0, and therefore y prime is bigger than 0, and therefore the y value here will increase in time. So we put this arrow. One can also sketch the solution qualitatively in the yt plane. So this is t-axis and this is y-axis. So first we identify the two equilibrium points. When y is 0 initially, it remains on it, the constant solution. And also, when y is 2 initially, the solution is constant. Then this cuts the plane into 3 pieces, and let's look at each of them. So on the part when y is less than 0, that's this part we discussed. And we see that y prime is bigger than 0. So solution here will increase, but it cannot cross this line because that's a solution. So it will increase and it will bend, it will approach 0. Okay, and then let's look at the interval between y is between 0 and 2 between these two horizontal lines. And here we see that y prime is this region, y prime is less than 0. So the solution is decreasing. So any solution here will go down, but it will not cross when y equals 0, and then it will just approach it asymptotically. And finally, the part y is bigger than 2 here, we see that y prime is bigger than 0 over here, and solution will be increasing, direction of field points upwards, so the solution will grow and grow and go all the way to infinity. So from this example, we see that for the two critical points, y equals 0 and y equals 2, nearby solutions behave very differently. So if you are in a small neighborhood around y equals 0, not too far, you see that the solution will return to y equals 0 as time grows and then approaches asymptotically. If that is the case, that is, if you perturb yourself a little bit from these equilibrium states, and then the state will return to the equilibrium state, and we call that stable. So y equal 1 is a stable equilibrium or a stable critical point. Now for y equal 2, it's very different. Y equal 2 is a solution, is an equilibrium, but then if you perturb a little bit, say you are a little bit bigger than 2, then you see the solution will keep growing and go away and go to infinity. And the same thing happens if you perturb it a little bit smaller. Say you have a value a bit smaller than 2, and then the solution here are decreasing. It will go further away from 2, and it will go to y equals 0. But you never return to the equilibrium y equal 2. Okay, so therefore we call this unstable. Okay, so I hope it's clear the definition of stability now. We call an equilibrium stable if it is stable with respect to small perturbations, meaning a small perturbation on the solution and the solution will return to the equilibrium. On the other hand, if a small perturbation around the equilibrium will make the solution go far away, not back to the equilibrium, and then we call it unstable. Okay, so that's all for this example. Okay, so now let's look at a different example. Now here we have y prime equaled fy, and we do not give an explicit expression for the fy, but we draw a graph which will give the qualitative behavior. So 3 questions. A, what are the critical points? And B, are they stable or unstable? And C, please sketch solutions in the ty plane and describe the behavior of the solution y as t goes to infinity, and describe how it depends on the initial value. Okay, so we can take a closer look at the graph of f of y, and we know the zeros are important. So this line f equal to 0 are dotted, and then we see that it crosses the graph 3 times. So there will be 3 critical points. One is 1, the other is 3, and the last one is 5. Okay, so an analysis of the graph showed us 3 critical points, 1, 3, and 5. And that's very simple. Now let's answer question B. What about the stability? Well, to figure that out, we can just look at the graph of f. We see that this is the graph, and we see that there are 1, 2, 3, 4 intervals of y value where f will have a distinct sign. So for y less than 1, and f is bigger than 0, so y prime is positive, solution increases, so we add an arrow. And then between 1 and 3, and the solution is negative, y prime is negative, the solution decreases. And between 3 and 5, f is bigger than 0, y prime is bigger than 0, solution increases. Okay, so the direction of the arrow is important. Okay, and then y bigger than 5, and f is less than 0, solution decreases. So we have all these arrows nicely pointed along the f equal to 0 line. Now we are ready to see the stability. Let's first look at y equal 1, the first critical points. If I perturb it a little bit to the left and to the right, what happens? Well, if I perturb a bit to the left and the solution will increase, it will return. And if I perturb it to the right and the solution decreases, and it returns. So you can see from the direction of the arrow, if it's a critical point where the arrow on the left and right are both pointing to you, then you are stable. Is there another critical point that has that same property? Well, we see that here. Y equals 5 is a critical point, and on the left and on the right, it has the arrows pointing towards it. So that's also a stable equilibrium. Okay, finally, let's look at y equals 3. That's an equilibrium. And then I see that on the interval left or interval to the right, we have marked arrows, but both arrows are pointing away from the equilibrium. This means if you have a little perturbation, say solution goes a bit to the left, it does not return, it will keep going more to the left. Or if you perturb it a little bit to the right, and then the solution does not return to the equilibrium, and it will increase and go away. So we see that this critical point here is unstable. Okay, now we can sketch the solution. Answer question C, which we actually knew how to do already from the study of the directional field. So this is T and this is Y. So 1, 3, 5 are the 3 equilibrium states. So these horizontal lines are solutions. And then for y less than 1, solution increases, approaches 1. Between 1 and 3, solution decreases, approaches y equal 1. Between 3 and 5, solution increases, approaching y equal 5. And for y bigger than 5, solution decreases and approaches y equal 5. Okay, and we can analyze asymptotic behavior. With this graph next to us, it's very clear. Okay, so we see that first, if y initially is less than 1, then it approaches 1. And then if y initially is 1, it's constant 1. And then if y is between 1 and 3, it approaches 1. Then if y is 3, it stays on it. And then next, if y is between 3 and 5, it approaches 5. And then next, if y is 5, it stays on 5. And the next one, if y is bigger than 5, and it approaches 5. Okay, so this is a very detailed list. One could probably lump them together. The first 3 cases, and the solution will all approach 1. That is, if y0 is strictly less than 3, everything approaches 1. And then y equals 3, the constant state. And then these 3 are the same also if y naught is bigger than 3, and then they all approach 5 asymptotically. Okay, that's all for this example. I hope it's all clear. Now next I would like to put some remark. This concept of stability, we have seen some examples. Those are simple examples. There are more complicated situations where it is not only stable or unstable. So allow me to explain in detail. Let's just take an example to see that it doesn't belong to the 2 cases we discussed already. Okay, so the equation is y prime is y squared. And we see that there's only one critical point, that's 0. And then let's analyze. If y is less than 0, y prime is bigger than 0, so the function will increase. But for y bigger than 0, we also have y prime bigger than 0. Solution also increase. So the solution will be increasing on both intervals, next left and right of the y. We can quickly sketch it. Let's say this is the y-axis and this is 0, and then the value on the left increases. We have an arrow, and y bigger than 0, and the solution also increases. Okay? And you can also sketch the solution in the yt plane. Let's say this is y, and this is t, and that's 0. And then we know that y equals 0, that's an equilibrium, so that's a solution. And then we see that, and if y is less than 0, it increases, so everything will approach. Solutions will be all approaching. But then if y0 shall be bigger than 0, then the solution also increases and it goes away. Okay? So we see that if we put a little perturbation around the equilibrium state here, if we perturb it a little bit so y becomes less than 0, and then it's stable, it goes back to 0 asymptotically. But if your perturbation is a little bit to the right of y, so y is a little bit bigger than 0, and then it will drift away to infinity and never return to y0. So it's unstable. So here is a new concept of this type of critical point. We call such a point is called a semi-stable. Okay, semi-stable means half stable, half unstable. So as we can see in this example, such a critical point would occur in the case where the f of y here has a double root at the critical point. Okay, so f of y is 0 and f of prime of y is 0, or polynomial to the power of 2 also. Okay, so with this new information in mind, and let's take a look at another example. So y prime is f of y, and f of y is given in this graph. Okay, so 4 questions. A, identify equilibrium points or critical points, and B, discuss the stabilities, and C, sketch solution in the yt plane, and D, discuss asymptotic behavior as t goes to infinity. Okay, so let's answer question A. So critical point is where f of y equals 0. So along this line we see it intersects the graph at 4 points. Here they are just equally spaced, and 0 and 1 and 2 and 3. Now let's look at the stability. Okay, and we can just add our arrows. So on this interval, f is bigger than 0, so pointing to the right. And on this interval, f is less than 0, point to the left. And on this interval, f is less than 0, point to the left. And on this interval, bigger than 0, point to the right. And on this interval, less than 0, point to the left. So we can go through each and see. So y equals 0, the arrows are pointing towards it, so it's stable. Y equals 1, that's the new situation. On the left is unstable, on the right is stable, so that's semi-stable. And y equal 2, on the left unstable, on the right unstable. They all point away, so unstable. And the last one, y equals 3, the arrows on the left and right both point towards it, so it's stable. Okay, and problem C, to give the sketch. So we can quickly give the sketch. We identify the critical equilibrium solutions, constants. We draw 4 of them, and we know the sign of y prime on each of these intervals cut by these 4, and we can just draw it. So for y less than 0, it increases, so it approaches. Between 0 and 1, it decreases, so it comes down. And between 1 and 2, y prime is less than 0, it comes down. And between 2 and 3 is bigger than 0, so it goes up. And for y bigger than 3, it's less than 0, so it comes down. Okay, so now we can give the asymptotic behavior. You can choose to discuss an interval by interval, here each, or you can observe and lump them together in groups. So first we see that if y0 is strictly less than 1, or here everything approaches 0. So that's this. And then we see that if it is less than 2, no, strictly less than 2, but bigger than or equal to 1, solution approaches 1. So that's this one. And then we see that y equals 2 is an equilibrium, it's unstable, but it's an equilibrium solution. So we have that. And then we observe that if y0 is bigger than 2, everything up here, they will all approach 3. So that's what we wrote. Okay, so we see that for autonomous equation, using this powerful tool as critical points and a quick analysis of the stability, we can sketch qualitative behavior of the solution very easily. It's basically the concept of directional field, but here is in a simpler setting of autonomous equation. And we can discuss asymptotic behavior also very conveniently. All this can be done without even trying to solve the equation or find an explicit form of the solution. All those are not needed, but we can say a lot about the solution behavior. Okay, that is all I have to say for this video. And in the next one, we will look at applications of the autonomous equation into a physical model of a population dynamic, where the application has been more interesting and more successful. So, and that's all. I hope you enjoyed it, and I'll see you next time.